Hello everyone. Hi, welcome back to the Oxford University Museum of Natural History for session 9B of this virtual Palaeontological Association meeting. So we've got a couple of minutes before the session starts, so some parish notices. If you have any connection issues, there is a reconnect button at the top of your screen. Just give that a click and you should that should get you straight back in. Please make full use of the chat feature over on the right hand side. Just say hello and let everyone know you're here. Also, if you have any questions for any of the speakers, please put them in there and mark them as a question by clicking on the little button to the right hand side of your question. So we have 5 fantastic speakers that will be giving 5-minute flash talks in this session, and at the end of that we will have some time for a question and answer session with all of the speakers. So any of your unanswered questions will be addressed in that last 10-minute portion right at the end. So we've just got another couple of minutes. Okay, it's 22 now. So if I can invite the first speaker, Lukáš, to turn on their camera and microphone. Hi, everything okay?
Yeah.
Okay, I'll get your slides.
Perfect.
Okay, thanks. Take it away.
Okay, thanks, Duncan, for introduction. Today, I'm going to be talking about some baby arthropods from Morocco. They are called marrellomorphs, and because they are closely related to famous and well-known Marella splendens from Burgess Shale. These marrellomorphs that I'm going to be talking about are not from the Cambrian. They are from the Ordovician. They are from the quite well-known lower Ordovician Lagerstätte called freshwater. Here in the first title slide, you can see the view over the main locality. You can see many of the holes in the background that were digged by local collectors, mostly by the family of Usaid Ben Mulla, also together with Peter van Rooij from Ghent. And so they collected plenty of these fascinating fossils. And among others, we have some juvenile stages, tiny little stages of these euarthropods from this locality. Just to be clear, the age is lower Ordovician, Araneograptus murray zone, so we are in the Tremadocean. Okay, so the adults are quite similar. Adults of this marrellomorph euarthropod that is still informally called Furca or Furca mauretanica, as was described by Peter van Rooij in his PhD thesis. Now I think that the name has changed. It should be Steno, but this is something David Leck is working on. So I'll just be very quick about to introduce you the morphology of the adults. So this marrellomorph arthropod from Morocco looks like that. You can see it's quite similar to Marella. It has an extra pair of spines in the front of the head shield. It has antennae. Then the second appendage is quite large, as you can see in the picture on the right side. And then the rest of the appendages, they are biramous limbs with endopods and lamellate exopods. The adults, they have quite a lot of segments, around 30. And you can see that on the spines that are protruding from the head shield, there are secondary spines. Okay, so we in the collection in the University of Lausanne, we have these we have babies of these marrellomorph arthropods from Ordovician, and we were lucky enough to be invited by Imran Rahman to scan some of these babies in the synchrotron in the Tomcat beamline in Paul Scherrer Institute in Switzerland. So we scanned this tiny little guy, and we can see that there are individual appendages actually, and the antennae, the second appendage. So we can see quite nice details. When you look at these tiny babies, you can see that the head shield is slightly different than in adults. It has more striated spines. The secondary spines are shorter, and there is less trunk segments. So we know that these arthropods were growing anamorphically. So they added segments during the development. But otherwise, the rest of the appendages are virtually identical with the adults. So when we consider the appendages, there was no major difference when compared to adults. So we actually think that these arthropods had rather direct development, at least from the stages from about 2 millimeters onwards. And so they were, based on the sedimentology, they were probably also inhabiting the same, the very same environment. So we're probably living in a very similar manner as adults. Okay, that's everything from my side. Thank you for your attention, and thanks to all organizers for this wonderful meeting.
Thank you very much, Lukáš. So any questions for Lukáš, please put them in the chat and we'll come back to them at the end. So we'll move on now to our second speaker. I'll just get your slides up for you, Ninon. There you go. So thanks very much, Ninon. You can take it away.
Thanks, Duncan, for introduction. So yeah, today I'd like to introduce you to this quite original arthropod that is on display at the Natural History Museum of Dublin. It was found in 1908, and since hasn't really ever been confidently assigned to any proper taxon. So these arthropod named Oxyuropoda, it was reported at the time from the site of Kiltorcan from County Kilkenny in Ireland, and from late Flaminian beds, so from the very late Devonian. And it was found in association with ferns and progymnosperm remains, as some are pointed out here by the arrows, as well as with freshwater placoderms and oysters, indicating a floodplain environment. And pretty different arthropod lineages were considered for Oxyuropoda, including arachnomorphs, eutychosinoids, phylocarids, or even peracarids, meaning the group of woodlice, as it actually has been the case for many arthropods recovered from that period. It has been also the case, for instance, for the famous millipede Arthropleura. It was considered apparently at the time an isopod when it was discovered as well. And this last possible assignment is pretty interesting because despite the pretty poor resolution of the phylogenetic relationships between the main peracarid clades, among the inner clades, like for instance among Isopoda, a diversification from shallow marine water to freshwater is apparently supported by molecular studies as early as the lower Devonian. So this fossil may come to question the actual timing of land colonization by peracarid various lineages. And reassessing the anatomy of Oxyuropoda is much constrained by its degree of flatness that really doesn't allow for any promising tomographic approach. And for that reason, we chose to investigate its anatomy using recent studied techniques like digital microscanning and multispectral macroimaging that is currently developed in Lausanne at the Anome Lab of Allison Daley by Dr. Pierre Gueriau. And the first technique allowed us, for instance, to observe in the head the actual appendages that corresponds to the mandibular, maxillary pieces, as you can see on your left side, or even the articulations of the euarthropods and the pleotelson of the animal. And beside the multispectral imaging, by producing these images on your right-hand side that select restricted range of issued luminescence, that did allow us to visualize the actual degree of thorax segmentation, as well as the animal ventral appendages, meaning structures that had never been observed so far. And these newly observed features allowed us to preliminarily place Oxyuropoda among a clade of peracarids that is gathering cumescins, tannids, amphipods, and isopods. This was obtained reusing morphological analysis gathering characters of modern taxa, as well as some specific telson characters from fossil taxa as well. And the oldest so far reported peracarid, that is known as Antcliffe, here in green, is early Carboniferous in age, and it was identified as a crown tannid itself, making Oxyuropoda the oldest crown peracarid and the oldest peracarid in general, because peracarids have no reported stem group so far. Plus, this crown lineage, it appears to have diversified before the divergence of isopoda and amphipoda. Therefore, Oxyuropoda make arguably wonder if isopoda amphipoda necessarily diverged in marine brackish waters as suggested, or if it could be as parsimonious to have them actually diversifying in fresh water before getting secondarily to shallow marine environments. So that's it for me. I thank you all for listening, and I want to warmly thank the Palace for accepting to support this project with one of their 2019 small grants. And that's it for me. Thank you.
Thank you very much, Ninon. Some more fantastic fossils, beautiful things. So again, we'll have questions at the end for Ninon. So if I'll bring up the next set of slides, and I'll hand over to Adiel to take us in a slightly more octopody direction. Thanks, Adiel.
Thank you very much for the introduction. So my name is Adiel. I'm the curator of paleontology at the University of Alabama. This work is in collaboration with Alex Kittle. He's a collections manager of the Delaware Museum of Natural History, and also in collaboration with Neil Landman, curator of fossil invertebrates at the American Museum of Natural History. This research was partly supported by the American Museum of Natural History Lerner Gray grant. So introduction to the topic, Octopodoidea are a superfamily of cephalopods living in nearly all marine habitats. This clade consists of about 250 species today. They are pretty abundant in many parts of the oceans. They are ferocious predators, really, that strongly affect prey density on many of the seafloors we know today. Today, they mainly consume mollusks and crustaceans, of which their shells or carapaces can be found commonly among piles in or around their dens. They often drill shell prey using their radula and salivary papillae, as well as venomous secretions coming from the salivary glands to paralyze and relax the prey's muscles for easier extraction. Next slide, please. Can I have the next slide? Thank you. So unlike the octopodoid abundance and diversity in today's oceans, very little is known about their evolution history. One of their main reasons is their soft body, which means they have a very low chance of fossilization. As a result, only one fossil species is known from the fossil record. This one has been described by Dirk Fuchs and colleagues from the early late Cretaceous or Cenomanian of Lebanon. However, we can use the drill holes to track the presence of octopodoids. These 0.1 to 2 millimeter size drill holes are often oval to subcircular and quite irregular in shape compared to the much more circular gastropod drill holes. Octopod holes are often ascribed to the trace fossil taxon Oegnus ovalis and sometimes Oegnus simplex. These predatory traces are severely understudied, and only 11 occurrences are known from the fossil record, as you can see on the upper left-hand figure. As a result, their stratigraphic range, abundance, and predatory behavior of octopodoids are pretty known. And here are just a few examples you can see in the images here. On the lower left-hand side, you see a barnacle from the Pliocene of Florida. On the upper right-hand side, you see a crab appendage from the Pliocene of Florida. And in the lower center, we see a bivalve from the early Eocene of England, which is the oldest one on the record so far. Next slide, please. Thank you. So we present two case studies here. First, in collaboration with Alex Kittle, I've studied about 2,400 Paleopleistocene cowries, or Cypriidae, from southern Florida. Cowries have never been studied for evidence of predation in deep time, surprisingly. So after we studied them, we found that 13.4% of all specimens had at least one octopod drill hole, whereas only 0.2% had a gastropod drill hole. So predation by octopod is fairly common, like in modern cowries. On the left, you can see that the octopod holes are predominantly located in the ventral left posterior, or VLP region, and also, but to a lesser extent, in the ventral left middle region, VLM region, even after normalizing the surface area per region. This is definitely not the thinnest part of the shell according to our measurements, but it is the attachment spot of the columellar muscle, which anchors the soft tissue to the shell's interior. Thus, this strong side selectivity in cowries evolved in or prior to the Pliocene. In upper right, you can see that the size of drilled shells does not statistically differ from non-drilled shells. So there is no size selectivity using this particular metric of size selectivity. Our results surely warrant the study of older cowries to assess octopod abundance and behavior. Next slide, please. Thank you. The second case study is in collaboration with Neil Lamon. In 2018, while I was studying a late Cretaceous Campanian methane seed fauna from South Dakota in the American Museum of Natural History, I discovered 3 glycinid bivalve specimens containing small oval to subcircular holes. They look identical to those produced by modern octopods in terms of size and shape, and no other animal is known to make similar sized and similar shaped drill holes. The existence of a body fossil of Octopodoidea in the late Cretaceous, as mentioned previously, and several phylogenetic analyses on modern octopods suggesting that octopodoids evolved in the Cretaceous also support a possibility that our drill holes here could be of octopod origin. Moreover, octopods are commonly observed near methane seeps today, as shown in the bottom center image. So in our view, these holes represent the oldest evidence of predation by octopods by 25 million years, extending their record from the Eocene into the late Cretaceous. This also implies that the ability by octopodoids to drill their prey evolved fairly early in their evolution history. So to conclude, our two case studies demonstrate that drilling traces produced by octopodoids are not necessarily rare, and that their fossil record should be leveraged further to study octopod occurrence and behavior. Thanks to all.
Thank you very much, Adiel, for a fantastic talk. Any questions for Adiel, please pop them in the chat and I'll come to them at the end. So we'll move on to our penultimate talk of this session. So I'll hand you over to Barbara Brent. Thank you, Barbara.
Hi, my name is Barbara and I'm a PhD student at the University of Liverpool, and today I'll be talking about reconstructing limb motion from fossil footprints. So fossilized tracks are direct evidence of how an individual was moving at a specific moment in time. So hominin fossil tracks are found all over the world belonging to different species. So the main figure on the left, the stars are indicating known hominin sites, So the oldest and most famous hominin tracks date to 3.66 million years ago, Laetoli, Tanzania, and are attributed to Australopithecus afarensis, and are highlighted on this figure here in green. So we can use footprints to infer body dimensions of track makers, such as their stature or body mass, and this is particularly useful when we're studying extinct species. So, for example, a study was done by Bishop in 2017. So the figure in the top right looked at footprints of modern humans, 11 species of ground-dwelling birds, and also extinct non-avian theropod trackways. And they looked at step width and found more similarities between the birds. So concluded that the theropod dinosaurs had a continuous locomotive repertoire rather than what we see in humans, where we have a specific gait for walking and running. So overall, studying footprints are good. However, there's many different interpretations of fossil tracks, which is highlighting the lack of understanding of how limb biomechanics and anatomy are recorded in footprints. And it's also important to consider the influence of the substrate material properties. So, for example, if you imagine you're walking on the beach when the tide is going out, if you're walking in where the sand is more dry, or if you're walking towards the sea where it's wetter, you notice that the imprint is slightly different. So to kind of answer these kind of questions, we investigated how footprints are formed in modern humans. So if you look at the figure in the top right-hand corner, this is depicting the different sand walkways that we used in this study. So we had two different types of sand. There's the children's playing sand and the building sand that is typically used in construction. So the play sand and what we've labelled here as building dry are of a similar moisture content. And then we also have the building wet, which is of a higher moisture content. And then we had participants walk over all three of these sand walkways, as well as a hard level floor. And we recorded 3D kinematics, muscle activity, and we also took lots of photos of the walkways to create 3D models using photogrammetry. So I'll just go over some basic results. So on the left, the main figures here are showing joint angles at the left ankle, knee and hip joint. It is from left heel strike to left heel strike. The vertical lines representing toe-off timings. But generally, you can see that there's some difference in the ankle joint here. The ankle joint plays a really important role in gait adaptations when we're walking on different surfaces, as it receives the whole body of the weight. And we're also seeing that on the more softer, more deformal substrates, that participants are sinking in deeper, and they're adopting a more bent hip, bent knee gait. So we are noticing that there are gait changes when we're walking over different substrates, but are these reflected in the footprints that are formed? So this is just based off the preliminary analysis. This was based off basic metrics such as foot width and foot length. And we're actually finding that there's a relative conservatism in shape as depth increases, which is suggesting that the changes that we've seen in gait from the previous slide may not actually be detectable in the footprint morphology. Which leads to the question, can we compare fossil footprints from different sites and dates and create an evolutionary sequence? Again, like I say, this is based off basic metrics. So the future work is to use the photogrammetry models to analyse complex 3D shape against kinematics. We may find that there's more smaller changes, shape changes that are indicating gait changes that we haven't picked up yet from using just the basic metrics. So that's everything from me today. Thank you for listening, and thank you to the organisers for their hard work.
Fantastic. Thank you, Barbara, for keeping so well to time. We're almost back on track. So for the last presentation of this session, we'll go from one fine museum to another and hand over to Liz in the Sedgwick.
Thank you. Brilliant talks to hear from everybody. Now for something, folks, completely different, just for the last 5 minutes. I'm going to talk a little bit about a couple of case studies of some work we're doing, myself and Rob Theodore, in the Sedgwick Museum and other colleagues there. We've had a lot of talk. I think there's been a lot of buzz around Palace, around where our specimens come from and decolonisation, and people uncomfortable about how and where some specimens have been collected. And I guess what I want to do today is just sort of do a historical sort of slant to that as well. Why does this matter, do you think? Why does it matter to be looking at these origins of the specimens? Well, I think the reason I think is that if we are serious about making our subject, our paleontology, something that is welcome and inclusive and accessible to everybody, we really need to address some of the things that exclude people, the sort of historical origins that might impact on people, and both in the present and in the past. So very quickly, 2 case studies that I want to talk about. These are quite difficult subjects, and I think they'll make us feel uncomfortable. They might make us feel unhappy. I often refer to them as uncomfortable histories because they're not always ones that we want to tell. And I suppose what I'm quite keen to do is make us feel comfortable about beginning to tell them. That's not to throw away the relevance when you've got specimens of difficult. It's not to say that their scientific importance isn't there, but it's recognising that there are important stories. And as a museum person, for me, it's really important to be telling that broader range about showing paleontology in its social and cultural context. So my first example, and if any of you were in the virtual field trip at lunchtime looking at Mary Anning specimens in Oxford Museum, well, we have some too in Cambridge, some that Sedgwick bought of Mary Anning. If you haven't heard of Sedgwick, he was important 19th century sort of a so-called father of British geology, or one of those many fathers of British geology, who was instrumental in setting up, for example, sort of basic lower Paleozoic stratigraphy, the Cambrian and Devonian, mentored Charles Darwin. He wrote a lot, and he talked about his abolitionist views. He had a hatred of slavery, as you see from the quote there. But also, that's where this character is quite ambiguous in our story, is that in 1836, he was a co-beneficiary. He received £3,783, the equivalent of about nearly £500,000 today, from the will of a slave owning family, Anne Sill in Dentdale. And you'll see the details there. She owned 174 enslaved people. And so the money of the Sill family was derived entirely from the labour of these enslaved people on Jamaican sugar plantation. And at this time, Sedgwick writes, the first time in my life I am to be well paid for my work. During the course of his lifetime, he bought and donated to the museum probably around 500,000 specimens. At the moment, the work that we're doing in progress is to try and understand when those were purchased, because we're fairly sure there's a big sort of peak in his purchasing. But it's pretty clear from the timings that at least these Mary Anning specimens, and I'm sorry, there's not really a scale, they're just there for decoration, but these Anning specimens are amongst those that he purchased at that time. My second example is a Belgian example, in fact, although you may know this iconic specimen, indeed it's the logo of our museum, is a cast of an iconic iguanodon from the Bernissart coal mines found in the 1870s. But look closely, and this, like a number of specimens given by the King of Belgium to Oxford, London seats of learning across Europe, it's donated by Leopold, King of the Belgians. Now, if you've read Heart of Darkness, Conrad's Heart of Darkness, you might have come across the sort of the horrific atrocities that took place in the 19th century in the name of Leopold's sort of colonial enterprises. The Congo Free State, what is now known as the Democratic Republic of Congo, was personally ruled by Leopold, an area of 2.5 million square kilometres, where he extracted rubber and minerals by enforced labour. Around 10 to 15 million Congolese people probably died between 1885 and 1908. And at this time he donated this, this was all sort of slowly coming to light. And it's fairly clear that Leopold was quite a sort of PR expert. And it's my speculation, at least, that this donation of these very high profile specimens to seats of learning around Europe was very much a PR exercise. So he's sort of using it as a way to curry favour with leaders of with European leaders. So I suppose I want to leave you with those sorts of questions. What's the history of the fossils you're working on? Where did that money come from? How do we tell these stories? How can we make sure that we're acknowledging that really quite troubling historical past? I'm really happy to answer questions, and there's more in the Discord chat as well around the legacies of colonialism and empire. Thank you.
Yes, thank you very much, Liz. That was a fantastic talk. So if I could invite all the speakers to turn on their cameras, and we've got 10 or 12 minutes or so, and I'll try and get to some of the questions in the chat. So first of all, Javier Ortega Hernandez was asking you, Lukáš, about the development of these critters. Do you want to add any more to what you've commented already in the chat? I won't read it all out because it's rather long.
I think I add most of the stuff in the chat. So, yeah.
Okay, no problem. Thank you very much. So, a question to you, Ninon, from Roy Plotnick about are there any candidates for STEM groups of your organisms?
Yeah, I did try to reply to Roy.
Sorry, yes.
There's nothing really that is coming to my mind. I was telling him about, in terms of morphology, what is probably things to look at would be the sister groups of eukaryotes and peracarids, which were anaspids and batinillids, basically those things that are put into syncarids. But first, those things should be probably not monophyletic themselves. And beyond, they're pretty different. So yeah, there's nothing really coming that could be a good candidate. Nothing so far.
Okay, we'll have to keep looking. And so moving on, a couple of questions to you, Adiel. First coming from Chris Little. So are there gnatid gastropods in the Campanian seep assemblages that could be alternative drillers of the leucinid shells, or do gnatid drill holes differ morphologically from octopoid drill holes?
First of all, apologies for the technical issues on my side. To answer the question of Crispin, thanks very much for the questions. Yes, there are gnatid drill holes in the same assemblages that I found. They differ very much in that the drill holes tend to be much more circular, on average larger in similar-sized shells, and they can be told apart pretty easily, actually. The octopod drill holes tend to be oval to subcircular, but very much more irregular. And then the gnatid drill holes, also the marrellomorph drill holes, tend to be much more circular in nature.
Great, thank you very much, Adiel. Another question to you, this one from Thomas Clements, who remarks it was an interesting talk. He asks, the molecular and fossil record indicates that early octopods were not benthic, although their record is very patchy due to the lack of fine mineralized skeletons. Other mollusks use similar predation. How do you verify that these are octopus traces?
Yeah, I was actually going back to the same answer. Most drillers today are gastropods, and those drill holes tend to be very circular in nature. They can be easily told apart. So the drillers I was talking about today are Octopodoid drills, Octopodoidea family, actually, which is one clade within the Octopoda, right? There's only one body fossil known in the entire fossil record from the Cenomanian of Lebanon. So indeed, we know very little of them because of their soft-bodied nature. We hope more of those fossils can be found, most likely in the Cretaceous, Larostetten, if they're still around. My guess is based on all molecular evidence so far, this Octopodoids is a clade, probably somewhere in the Cretaceous when it evolves.
Super, thank you very much. So a question to you, Barbara, from Matteo. He says, excellent presentation, and quick question, does the internal morphology of the track, is that the same among different gates? And he thinks it should be should be more variable than a simple length and width.
So between the different walkways, they were definitely noticing some differences. For example, when you're in softer surfaces, like when your toes leaving the surface of the sand, there's definitely going to be more sand like kicked back into it. That's going to affect the shape of the internal morphology. But like I said before, we've just done the preliminary analysis. definitely wants to look at more complex shapes, so using like SPM, which is going to use a pixel by pixel comparison, and definitely pick up more of the differences, hopefully.
Super, thank you. We have a follow-up question about these to you, Ninon. Thomas Laibl asks, are there other enigmatic or problematic fossil taxa that could be related to the Oxyuropoda?
They could be, simply because what I didn't say is that the interpretation I presented today of Oxyuropoda is one way to interpret it. There could be a very different one based on the amount of segments you actually see from the thorax, because the thorax is made of many, many parts that could correspond either to true segments or to ornamentations. So it's a big jigsaw to work with. And if that is another version than the one I did presented today, it could be related to many other pretty problematic specimens. So that's something that's really still ongoing. But it is the most likely would be to have that interpretation that put it into peracarids, the most likely one.
Brilliant, thank you, Ninon. And returning to the drill holes, question from Mario to Adiel. Do you think it's possible to identify octopus drillings based on morphometric parameters?
Great question. Well, one of the blessings of octopod drill holes, if you can call it a blessing, is that the morphology is very variable, even those octopod holes made by a single individual, which means that they can be relatively easily distinguished from gastropod drill holes, actually. They tend to have a gutter sometimes. Sometimes they're star-shaped. They're so variable. I don't think you can use geometric morphometrics or any type of morphometrics to distinguish them statistically from drill holes made by gastropods. But again, morphological variability is a blessing in this case.
Fantastic, thank you, Adiel. Now, Liz, we've had a lot of comments saying how great the talk was, and people are asking for more. So, Liz, thank you for posting a link there to some more information you provided. One specific question that's come from Chris Docker. Do you think there are any possibilities to combine the decolonization of fossil collections with outreach, perhaps to attract indigenous people to paleontology?
Absolutely. I think it's a really, really good question. And I think the question of sort of working with people from countries and places of origin and communities of origin is absolutely fundamental to proper sort of engagement. Of course, and Christopher, I don't know where you're coming from. The situation's different in different countries. If we're talking about European collections, is it going back working with countries that were colonized? Certainly in the chat, there's some interesting discussion about working with fossils taken from Native American lands. But I think any of that sort of the principle of recognizing that these are people whose knowledge and expertise and ownership in some cases, whose lands have been forgotten, to engage them and to hear views is really, really important if we're going to do this properly, both involving them in science, but also involving them in outreach and engagement. Yeah.
Fantastic. Thank you very much, Liz. And with that, I'd like to encourage everybody who's interested in this to move over to the Discord, where there is a specific paleoethics channel as well, where we can continue this. And talking of the Discord server, it's now the poster session. So please head over to the Discord channels to check out all the amazing posters. And then after that, you can come back onto Webinar Jam for always the highlight of the conference, the AGM. So with that, I'd like to thank the speakers again, and thank you all for your attention.